Good morning, all of you. Welcome to Sri Jayendra Rank Zone. In the previous lecture, we have done in coordination compounds, lecture 3. In that lecture, we have done Werner's theory as well as optical isomerism and questions based on isomerism and Werner's theory. Now, in this lecture, we are going to discuss new concept that is valence bond theory. Very, very important. Please note down. Definitely, you are going to get questions from this topic. This chapter is very, very important. Every entrance exam, it will give you minimum 2 or 3 questions from this chapter, from this topic. Even for IIT advanced also it is important. Mains also it is important. Neet also it is important. So that's why it is very, very important. I'm giving it you the best lectures so that you can understand the concept easily. That's why we are doing more questions also. Next, next concept in this chapter, that is various theories. First we have done valence bond, that is Werner's theory. Now second theory is valence bond theory. Now we are going to discuss valence bond theory. Please see that it was proposed by L. Pauling to explain hybridization. Now we have come into new topic in this coordination compounds, the hybridization and shapes of complexes. So this theory will give you the hybridization and shapes of complexes. According to this theory, the metal atom or ion under the influence of ligands can use its n-1 d orbitals, ns orbital, np orbital, or ns, np, nd, mt orbitals for hybridization. So that's why most of the transition metals will form complex compounds, because due to their having n-1 d orbital, ns orbital, np orbital, or they have ns empty orbital, ns np empty orbital, and nd empty orbital for hybridization. This point is very, very important, children. Please note it down. To yield a set of equivalent orbitals of definite geometry, such as octahedral, tetrahedral, square planar, and so on. These hybrid orbitals are allowed to overlap with ligands, that is electron donors, orbitals that can donate electron pairs for bonding. So this theory is basically based upon shapes and hybridization of coordination compounds. From this valence bond theory, what we'll get the shape and hybridization of complex compounds, coordination compounds. Very, very important. Please note it down. So it's very simple also, just like chemical bonding, but here it is different. Under the influence of strong field ligand, here we have to see weak field ligand and strong field ligand. What is strong field ligand? What is weak field ligand? We'll discuss now. The electrons can be forced to pair up against Hund's rule. So under the influence of strong field ligand, the electrons can be forced to pair up against Hund's rule. And if a complex contains unpaired electrons, the complex is paramagnetic. Unpaired electrons mean it contains, definitely it is paramagnetic. And if all the electrons are paired, the complex is diamagnetic. So paramagnetic complexes we have as well as diamagnetic complexes. The number of empty orbitals that can undergo hybridization is equal to the coordination number of the central metal atom. Very, very important. The number of empty orbitals that undergo hybridization is equal to the coordination number of the central metal atom. So these are the few postulates of valence bond theory. Continuation. So if the metal has coordination number 4, it undergoes what type of hybridization? sp3. This table is very, very important. You will get question from this table. So if the metal has coordination number 4, it will undergo sp3 hybridization and the shape is tetrahedral. Similarly, if the metal has coordination number 4, it can also undergo dsp2, means d orbital is involved, and it has a shape square planar. Example, in the case of platinum Cl4 2 minus, platinum Cl4 2 minus. So in this, what happens? The number of coordination number is 4 because it contains 4 ligands and its shape is square planar. Similarly, it has, if it has 5, coordination number is 5, sp3d, trigonal bipyramidal, just like in the case of chemical bonding compounds, inorganic compounds. Similarly, if the metal has coordination number 6, it has hybridization sp3d2, and the shape of the complex is octahedral. And one more complex is also can be found because of the involvement of transition metal complexes. We have D2sp3 hybridization. It has a shape of octahedral. So octahedral, we have 2 types of hybridations possible. One is sp3d2, another is D2sp3. So if d electrons are involved in bonding, definitely it will undergo D2sp3 hybridization. And if d electrons are involved in bonding in coordination number 4 type compounds, they have dsp2 hybridization. So these two are very, very important. So dsp2 as well as d2sp3. So you have to concentrate more on these two compounds, remaining all the same like chemical bonding. So please listen carefully. So what is the valence bond theory gives you? The shape and hybridization of the complex compounds. Just simple. Now application of valence bond theory for octahedral complex. So let us see cobalt, hexaamine cobalt 3, hexaamine cobalt 3. This is a complex and atomic number of cobalt is 27. Oxygen state of cobalt is +3 because it is shown already +3 here. And the electronic configuration +3 cobalt means what is the atomic number of cobalt? 27. So 3d7 4s2. What is the hybridization here? 3d7 4s2, and it has actual cobalt and +3 configuration is 3d6 4s0. 2 electrons from s orbital and 1 electron from d orbital is going off. So this is called hexaamine cobalt 3. Hexaamine. Just electronic configurations are very important. So since cobalt +3, it has 3d6 configuration 4s0 4p0 are 4s is 0 and 4p also empty. So ammonia is a strong field ligand, very important. Since ammonia is a strong field ligand and hence the electrons are paired up against to Hund's rule, then the cobalt atom undergoes hybridization to give 6 empty hybrid orbitals which are oriented towards 6 corners of regular tetrahedron, 6 corners of regular tetrahedron, and the hybridization is d2sp3. D2 because these two d electrons, one s electron and p3 orbitals. So this is d and this is s and this is p. So d2, 1s and 3p orbitals will undergo overlapping with each other and forms d2sp3 hybridization. So what is the hybridization of cobalt ns3 taken 6 times? That is nothing but d2sp3 hybridization because d configuration, d electron of the cobalt is involved in the formation. So that's why it is very important. Please try to understand. It is forming ammonia is a strong field ligand and hence the electrons are paired up against one rule. So in all the 6 places ammonia is being formed. So then the cobalt atom undergoes hybridization to give 6 empty hybrid orbitals which are oriented towards 6 corners of a regular tetrahedron, and these all corners will be occupied by ammonia. All corners will be occupied by ammonia. So due to which what happens, it forms cobalt hexamine. These hybrid orbitals will overlap with fulfilled orbitals of nitrogen atom of ammonia to form 6 coordinate bonds. How many coordinate bonds? 6, because nitrogen, each nitrogen will have 2 bonds. So total we have 6 nitrogen. So 6 nitrogen, 6 pairs of electrons will form to form 6 ammonia molecules. 6 ammonia molecules. So this is the explanation of valence bond theory for the octahedral complex. Next, properties of the complex. The complex is diamagnetic complex as the electrons are paired. As all the electrons are paired, you can see in the previous slide, as all the electrons are paired, even cobalt as well as this, since all the electrons are paired, so this configuration definitely should understand clearly. These hybrid orbitals will overlap with fulfilled orbitals of nitrogen atom on of ammonia to form 6 coordinate bonds, and this is the formation of 6 cobalt. So since all the electrons are paired, the complex is diamagnetic complex. Since all the electrons are paired, the complex is diamagnetic complex as the electrons are paired. And as there is no unpaired electrons, the magnetic moments. What is how to calculate magnetic moment? Mu is equal to root of n into n plus 2, where n is equal to number of unpaired electrons. Where n is equal to what? Number of unpaired electrons. This already we know. Since many classes we are learning this. So number of unpaired electrons. Hence, the magnetic moment is 0. The complex uses inner d orbitals, that is 3d orbitals for hybridization, and hence the complex is known as inner orbital complex. Since it is using d electrons, it is called inner orbital complex. Definitely, they'll ask you the question: which of the following is inner orbital complex? Which of the following is outer orbital complex? Due to the presence of strong field ligand, the electrons in d subshell undergo pairing against Hund's rule, and the net spin decreases. Hence, the complex is termed as low spin complex. Very important. All these points are very important. These are the properties of the complex CO it is taken 6 times. Due to the presence of strong field ligand, this is field ligand, the electrons in d subshell undergoes pairing against Hund's rule, and the net spin decreases. Hence, the complex is termed as low spin complex. So, inner orbital complexes are low spin complexes. Inner orbital complexes are low spin complexes, and which are called as inner orbital complex. If d electron are involved, since n minus 1 d electrons, 3D subshell n minus 1 d electrons are involved, since n minus 1 d, that is 3D subshell, is involved for hybridization, hence the complex is known as inner orbital complex. Please note down, this is very, very important. Next, continuation. Next, coming to this, let us see this compound, that is cobalt hexafluoride -3. So hexafluoro cobaltate, cobalt. The atomic number of cobalt is 27, as we already know. The electronic configuration is argon 3d74s2. And oxygen state, since it is -3. So how to calculate oxygen states, already I showed in the first video itself. So this is x plus -1 into 6, because flow in oxygen state is -1, since already we know, is equal to -3, implies x is equal to -3 plus 6. So it is equal to +3. So in this way you can calculate oxygen state. So the oxygen state of cobalt is +3. So the configuration of cobalt is 3d64s0. 3d64s0. Now let us see how it will form the compound. So again, the same thing here, 4s is empty, 4p is empty, and 4d is also empty. So since fluorine is a weak field ligand, so we should understand weak field ligand bonding is different, and strong field ligand bonding is. Hence, the electrons are not paired against to Hounslow. So thus cobalt plus the ion undergoes sp3d hybridization. sp3d, yes, 3p orbitals and 1d orbital. So sp3d hybridization, sp3d2 hybridization, by making use of 4s, 4p, and 4d orbitals. So these 4s, 4p, and 4d orbitals will undergo hybridization and forms sp3d2. sp3d2. Please note down here, very, very important. Here, since wherever weak field ligands is there, outer complex. Strong field ligands, inner orbital complex. Weak field ligands, outer orbital complex. Very, very important. So if you know weak field ligand, outer orbital complex, and the strong field ligand, inner orbital complex. Please note that. So these empty hybrid orbitals now overlap with full filled orbitals of fluoride ion to form 6 coordinate bonds. How many coordinate bonds? 6 coordinate bonds. So here D will be 3d6 will be there, then 4s2, so 4p3. So 6 pairs of electrons form 6 fluorine ligands. So this is the bonding taking place. So all are completely paired. 1, 2, 3, 4, 5. All are completely paired. So the complex has 4 unpaired electrons, hence it is a paramagnetic complex. You can see here, it has how many unpaired electrons? 1, 2, 3, 4. So since it has 4 unpaired electrons, because 4s and 4p will be filled, and it has 4 unpaired electrons. Since it has 4 unpaired electrons, it is paramagnetic in nature. Paramagnetic in nature. So easily we can calculate the magnetic moment by using the formula mu is equal to root of n into n plus 2. Mu is equal to root of n into n plus 2. So the complex has 4 unpaired electrons, and hence it is a paramagnetic complex. As it has unpaired electrons, it is a paramagnetic complex. It will exhibit color also, and the magnetic moment of the complex is given by mu is equal to root of n into n plus 2, where n is the number of unpaired electrons. So the magnetic moment of the complex is 4.89 Bohr magneton, because 4 into 4 plus 2, that is 4 into root of 24, root over 24 is 4.89. Bohr magneton is the unit of magnetic moment. I hope it is clear. Continuation now. Next, application of EPT for octahedral complex. The complex uses outer d orbitals, 4d subshell, and hence it is known as outer orbital complex. As I told you, simple, you can understand weak field ligand, outer orbital complex, This also they'll ask in examination. That's why you should understand which are strong field ligands and weak. Strong field ligands, inner orbital complex. So the complex uses d orbitals, outer d orbitals, 4d subshell, and hence it is known as outer orbital complex. The electrons are not paired against to Hounslow, so and the spin is high, so it is high spin complex. So weak field ligand, outer orbital complex, high spin. Strong field ligands, inner orbital complex, low spin. So please note down the complex has octahedral shape due to sp3d2 hybridization. So COF6 taken 3 minus is undergoing sp3d2 hybridization. sp3d2 shape is octahedral. And for every molecule, if you write like these points, it is easy for you to understand. And in the examination from this only they'll ask. So COF6 taken 3 minus undergoing sp3 hybridization, shape is octahedral, and it is outer orbital complex, outer orbital complex, and also it is high spin complex, high spin complex. And fluorine minus is weak field ligand. Weak field ligand. So these are the main points which you are going to get in the examination. So they undergo sp3d2 hybridization, octahedral shape, and weak field ligand. Since F minus is weak field ligand, it will form outer orbital complex and high spin complex. So these are the things which you are going to, and this is not against to Hounslow. It is paired against, not against to Hounslow. It is paired according to the Hounslow. So very, very important. Please note it down. All these points, please note it down in your classwork. Easily you can understand. These points are very crucial in the examination. They are going to ask about this only. Either they ask us hybridization, or they ask us shape, or they ask us weak field ligand, or they ask us whether it is outer orbital complex, or whether it is having high spin or low spin, outer orbital or inner orbital, weak field ligand or strong field ligand. Shape and hybridization will never change. So I hope it is clear. Next continuation. Very, very important, this valence bond theory. So let us see next molecule, molecule number 3, nickel cyanide taken 4 times 2 minus. All these molecules, they are given in NCRT. So based on NCRT only, you are going to get questions in the entrance examination. So that's why we are giving the best molecules. So please note down all these molecules. So nickel tetracyanonickelate 2, tetracyanonickelate 2. So we can have atomic number of nickel is 28. Electronic configuration of nickel is 3d8 4s2. So this already we know. Now oxygen state of nickel is +2. So 2 electrons are removed from s orbital. So we have only 3d8. Let us see now how does it forms complex. So 3d8 means 2, 4, 6, 7, 8. So 2 unpaired electrons. Now cyanide is a strong field ligand. Since cyanide is a strong field ligand, as I told you, ligands, based on ligands only we can have the complex, and the electron pairing takes place against to Hounslow. So if there is a strong field ligand, automatically the electron pairing takes place against Hounslow. So this total, how many cyanides we have? 4 cyanides. The nickel metal metal ion undergoes dsp2 hybridization. What type of hybridization? dsp2. So d orbital, 1 s orbital and 2 p orbitals will undergo, and to form 4 empty hybrid orbitals which are directed towards the 4 corners of a square plane. So 1, 2, 3. So total here 1d, 1s and 2p orbitals. So dsp2 hybridization, dsp2 hybridization. So which is going to form square planar complex. So now these empty hybrid orbitals will overlap with fulfilled orbitals of carbon atom of cyanide ions ligands to form 4 coordinate bonds. D is completely filled. 4 pair of electrons from 4 CN ligands also will be completely filled. Since it is all are paired, diamagnetic complex as the electrons are paired, inner orbital complex as inner d orbitals used for hybridization. Whenever d is electron is involved, so it is inner orbital complex. So if you know the hybridization, easily you can find out it is suppose if it is d2 dsp2 or d2sp3, we can say it is inner orbital complex. Or suppose if they have strong field ligand, they also will, strong field ligand is there. So they also can form inner orbital complex, and they are parametric in nature. So low spin complex as the electrons are paired against to Hounslow. dsp2 hybridization shape is square planar shape. So all are interrelated. That's why it is very, very important. So either if you know the hybridization, you can find whether it is strong, you can find the shape, or by the shape you can find the hybridization. So hybridization is key factor, or otherwise if it is strong field ligand, easily you can go, it is for dsp. Inner electrons are involved. Since inner d orbital electrons are involved, So it is called as inner orbital complex. Inner orbital complex. So all these cases are very, very important. So please listen carefully. Easily you can understand. So d-sp hybridization has square planar shape. Next continuation. So next molecule will take molecule number 4, tetrachloronickel 82. So atomic number of nickel is 28. The configuration is same. Oxygen state of nickel is +2 here because how to find oxygen state as I already told you. X plus -1 is oxygen state of chlorine into 4 times is equal to -2 implies X is equal to -2 plus 4 which is equal to +2. So oxygen state of nickel is +2. So here we can find the oxygen state. So since the oxygen state of nickel is +2, it is 3d840 because electrons from s orbital will go first based on Hund's rule. So continuation now. Let us see the shape of this molecule. Again, it is square planar complex only, but it undergoes what type of hybridization? Let us see. Since chloride ion, very, very important. Please see here. Fluorine is a weak field ligand. Chlorine is also a weak field ligand. So no pairing of electron takes place. The nickel ion undergoes hybridization to form 4 empty hybrid orbitals which are directed towards 4 corners of a regular tetrahedron. So 1, 2, 3, 4. So 4 sp3 hybrid orbitals. So due to which what happens, it forms outer orbital complex. Since d electrons are not involved, it forms so 4 pairs of ligands. So these hybrid orbitals will overlap with full filled orbitals of chloride ligands to form 4 coordinate bonds. How many coordinate bonds? 4 coordinate bonds. And these coordinate bonds are nothing but, so they form 4 coordinate bonds. So NaCl4 has, this is the configuration, 4 pairs of electrons formed, ligands. Now let us see. So paramagnetic due to the presence of 2 unpaired electrons. Since it has 2 unpaired electrons, you can just check here 2 unpaired electrons are present in d orbital. So it is paramagnetic in nature. So magnetic moment is 2.8 Bohr magneton. The complex is high spin complex and also it is outer orbital complex, high spin and outer orbital complex. Outer orbital complex. They'll ask definitely in the examination which are the following is outer orbital and which are the following is inner orbital complex. The complex is tetrahedral in shape due to sp3 hybridization. So hybridization is sp3. So like these questions they'll ask in the examination. So that's why we have given based on NCRT. Next, magnetic properties of complexes. The magnetic moments of coordination compounds are measured by magnetic susceptibility experiment. The magnetic moments of coordination compounds are measured by magnetic susceptibility experiments for the metal ions with up to 3 electrons in the d subshell. This point is very, very important. Up to 3 electrons in the d subshell, like titanium plus 3, D1 configuration, vanadium plus 3, D2 configuration, chromium plus 3, D3 configuration, D3 configuration, have 2 vacant d orbitals, since already we know, because up to 3 electrons means this should go like this 1, 2, and 3. So fourth and fifth are empty. So that's why they have 2 vacant d orbitals available for hybridization. Hence, the magnetic behavior of these free ions and the coordination entities will be the same. For metal ions having more than 3 electrons in the d subshell, 2 vacant d orbitals is not directly available because already they have 5 electrons will pair it up. So more than 3 electrons in the d subshell, they will not be available. Hence for D4, like chromium plus 2 Mn plus 3, D5, D6, a vacant pair of d orbitals are available only by pairing of 3d electrons against 2 Hund's rule. So in certain complexes, so best point here we have, in certain complexes with metal ion having D4, D5 configuration, there is some anomaly in magnetic behavior. The complex MnCN is paramagnetic with 2 unpaired electrons. MnCl6 3 minus is paramagnetic with 4 unpaired electrons. FeCN taken 6 times 3 minus is paramagnetic with 1 unpaired electron. And FeF6 3 minus is paramagnetic with 5 unpaired electrons. So by this we can say complexes with metal ions having D4, D5 configuration, D4 and D5. D4 is Mn plus 3 state and D5 is Mn plus 2 state, Fe plus 3 state. and D6 is Fe plus 2, CO plus 3. So here, what is the oxygen state of manganese? Here it is plus 3. So it is paramagnetic with the 2 unpaired electrons. And while MnCl, so that is what type of configuration is with 2 unpaired electrons? It is D5 configuration, Mn plus 2, no? So Mn plus 3 configuration is nothing but D4 configuration. D4 configuration, this is D5 configuration, this is also plus 3 state. This is again iron plus 3 state. Iron plus 3 state is D5 configuration, and FeF6 is paramagnetic with 5 unpaired electrons because it is plus 3 state. So iron plus 3 state is paramagnetic with 5 unpaired electrons, and here Fe plus 3 is paramagnetic with 1 unpaired electron. Here it is very, very important. Fe plus 3, it is having D5 configuration with 1 unpaired electron, paramagnetic. So this is very, very important point. So based on number of unpaired electrons, we can find easily magnetic moment, that is mu is equal to root of n into n plus 2. So finding number of unpaired electrons is most important. So this anomaly is explained by valence bond theory in terms of inner orbital complex and outer orbital complex. So this why D1 and D5 are showing different this thing. So this anomaly is explained, that problem is explained by valence bond theory in terms of inner orbital complex and outer orbital complex. The complex is manganese. This is plus 3 state of manganese, iron plus 3 state, and cobalt with oxalate ion. So our inner orbital complex with the D2 sp3 hybridization, and the complex is MnCl63 minus FeF63 minus COF63 minus, and MnCl3 minus FeF6 COF6 are outer orbital complexes with sp3 hybridization, sp3d2. So the number of unpaired electrons is same in both the cases, but it is inner orbital complex as well as outer orbital complexes. So very, very important this point. So please note down. So in general, how to identify which is inner orbital, which is outer orbital depends upon the weak field and strong field. So I'll give you a list of weak field ligands and strong field ligands. What are the limitations of valence bond theory? Valence bond theory successfully explains the formation, structures, and magnetic behavior of coordination compounds, but it does not explain the color exhibited by the coordination compounds, the stability of complexes, the difference between weak and strong ligands. It does not make exact predictions regarding the tetrahedral and square planar structures of coordination number 4. So which will undergo sp3 hybridization, which will undergo dsp2 hybridization, he could not explain. So these are the limitations of valence bond theory. So valence bond theory limitations also, they'll ask statement based question. Which of the following is true regarding valence bond theory? Which of the following are the limitations of valence bond theory? So they'll ask like these statement based questions. So what he could not explain, the color exhibited by coordination compounds, stabilities of complexes, difference between weak and strong ligands, and it does not make exact predictions regarding this. Just he said weak field ligand, strong field ligand, but how the difference between weak field and strong field ligand, how they are classified, he could not explain, and he does not make exact predictions regarding the tetrahedral shape and square planar structures of coordination number 4. Very, very important. So please note it down. Next continuation. So now we are going to discuss questions based on valence bond theory so that you'll be perfect with it, and then we can end this session. So I'm doing the share screen for you. So please note it down. Now we are going to discuss questions based on valence bond theory. So here I'm writing questions on valence bond theory, PPT. Very, very important. So that's why I'm giving you slides also. Best questions I have selected. So we are going to discuss that questions only now. So easily you can identify which type. So many complexes they can give, but we need to identify which are outer orbital complex, which are inner orbital. So what type of questions you are basically getting from this, we are going to discuss now. So which of the following is outer orbital complex? Question number 1, as I told you, which of the following, which of the following is outer outer orbital complex? The following is outer orbital complex. Let us see now. Option 1, cobalt hexafluoride 3 minus. Simple, easily you can say now. Option B, copper water taken 6 times plus 2. Option C, cobalt NH3 taken 6 times plus 2. Both 1 and 2. Option D, both 1 and 2. So that is both A and B, sorry, both A and B. Both A and B. Now, how to answer this type of questions? Let us discuss now. Solution. So based on valence bond theory, we can understand which of the following is outer orbital complex. Since flowing and water are weak field ligands, we'll give you the list of weak field ligands and strong field ligands. They form outer orbital complex because outer electrons are involved in the bond formation. So outer orbital complex. Outer orbital complex. This is the answer. So please note down. For this is the answer now. So option is fourth option. Directly you can say that is D option, both A and B. Why both A and B? Because NH3 is strong field ligand, so it forms only inner orbital complex. Since NH3 is strong field ligand, it forms only inner orbital complex. So answer is first and second, that is both A and B. That is fourth option, that is D option. I hope it is clear. Very, very important. We have to know the weak field ligands and strong field ligands. Next, question number 2. Let us start now. sp3d2 hybridization. sp3d2 hybridization. So weak field ligands forms outer orbital complex and high spin complex, and they'll go hybridization normal. So sp3d2 hybridization is present in, as I told you, all the 4 points in valence bond theory is important. So is present in option A, COF6 taken 3 minus. Option B, NiCO taken 4 times, that is nickel carbon tetracarbonyl. Option C, it is cobalt hexamine. Cobalt. So here I write cobalt with the nearby. So that you not get confused. Cobalt hexamine plus 2 is the charge. And option D, it is nickel cyanide minus 2. So now what is the right option? Since already you know cyanide is strong field ligand, ammonia is strong field ligand. So strong field ligands will form inner orbital complex, and inner orbital complex means d orbital will involve. So since d orbital is not involved here in the means d orbital directly is not involved directly. So that's why the answer for this could be, so either A and B, because C and D are ruled out. So C and D are ruled out, but then again carbon, nickel carbon, the oxygen state of nickel is 0. So it has no this thing hybridization. So answer for this is first option. That is, what is the hint now for this? The solution is, straight away we can say, weak field ligands with coordination number 6. So weak field ligands will form outer orbital complex. Why I am writing again and again? So that you can understand easily. You'll know how to identify the question, how to go for your answer. So weak field ligands forms outer orbital complex, very important, and they'll undergo hybridization. Coordination number is 6. Coordination number 6 means they will undergo hybridization, sp3d2 hybridization, sp3d2. Here the coordination number of coordinate cobalt is 6 because 6 fluorines are attached to it. So coordination number is 6. So coordination number 6 means definitely it should have either D2 sp3 or sp3d2. How to identify whether it is D2 sp3 or sp3d2? So D2 sp3 means strong field ligand should be there and it should have inner orbital complex because outer orbital complex will be according to Hunt's rule as they are according to Hunt's rule, whereas inner orbital complex is against to Hunt's rule. So that's why this answer is first option. So according to Hunt's rule only they are forming, that is s orbital, p orbital and d orbitals. So outer orbital complex means according to Hunt's rule. Inner orbital complex means against Hunt's rule. So whenever they go against Hunt's rule, so D2 sp3 will form. And coordination number is 6, how can we say? Because the coordination number is 6 and here the coordination number is 4. Here also coordination number is 6, but since ammonia is strong field ligand, you can also see the coordination number of cobalt with ammonia is 6 here because 6 ligands are attached directly to cobalt. But still, since ammonia is a strong field ligand, it will form inner orbital complex. When inner orbital complex is formed, automatically it will go against to Hunt's rule. So definitely D2sp3. So this is definitely D2sp3. And this is again coordination number 4. So no need to see these two. Only option A and C can be the connectivity. But why option A is only correct? Because weak field ligands outer orbital complex and they'll go according to Onson and they form sp3d2. So please note down these are the things which we are going to discuss. Next question number 3. Very, very important this concept. So the type of hybridization, simple this question also. The type of hybridization, easily by seeing this question easily can guess. Present in cube copper NHT taken 4 times plus 2 ion is option A sp3, option B dsp2, option C sp3d, and option D sp3d2. So first we need to see the coordination number. What is coordination number? The number of ligands attached directly to the metal is called its coordination number. So for this, the coordination number for this compound is equal to 4. So definitely it should have either sp3 or dsp2. So C and D are ruled out. So it will have either sp3 or dsp2. And how can we identify whether it is sp3 or dsp2? Straight away, since ammonia is strong field ligand. Ammonia is strong field ligand. So since ammonia is strong field ligand, definitely it will have what type of inner orbital complex? Inner orbital complex, low spin complex, inner orbital complex with low spin. It will undergo low spin, and definitely this should be dsp2 because they form against Hunt's rule. Against Hunt's rule. They formed against Hunt's rule. So answer is option B. Very, very important. So like these questions you may expect in the examination. So with the ligands, type of ligands, we can answer whether it is strong field ligand or weak field ligand, whether it is inner orbital complex, outer orbital complex, low spin or high spin, and hybridization. So by the means of coordination number, by seeing the complex easily, we can find the coordination number because number of ligands attached to the complex is called, attached to the central metal atom is called its coordination number. So the coordination number of copper in this molecule is 4. So definitely if the coordination number is 4, there are the chances of either sp3 or dsp2. So to identify whether it is dsp2 or sp3, so simply we have to see whether the copper is attached to strong field ligand or weak field ligand. If the copper is attached to strong field ligand, it will definitely undergo inner orbital complex and also form low spin complex, due to which it will undergo against Hunt's rule and form pairing takes place against Hunt's rule. So pairing takes place, pairing of electrons will be against Hansul, so automatically it will go for DSP2. So answer is second option. What is the answer now? Second option. So it is clear now. Next question. So please carefully observe these questions. Question number 4. All these questions are very important models. That's why I'm discussing now. The hybridization. This is also simple. The hybridization of metal atom and geometry. The hybridization of metal atom and geometry of the complex silver NH3 taken twice plus simple it is. Since coordination number is 2, we can say the shape of the molecule is sp or linear. Option B, it is sp2 linear. Option C, it is sp2 trigonal planar. And option D, it is sp angular. Sp comma angular. So how to identify this type of questions? Very simple idea I'll give you so that easily you can understand. Definitely, since it has coordination number 2, since coordination number is equal to 2, either it will undergo, definitely it will undergo sp hybridization. So sp hybridization, we have only two options, that is A and D. Now we have to see, since ammonia is strong field ligand, strong field ligand. So inner orbital complex. So it will undergo, since coordination number is 2, it will undergo sp hybridization. Sp hybridization shape is only linear. When it could be angular if it contains unpaired electrons. So it is linear. So option is first option, that is A, sp linear. So please note down, these type of questions are most important. Definitely they are going to get these type of questions in the examinations. Next, question number 5. So I want to discuss all the types of questions with valence bond theory so that you can be perfect with this. That's why I'm discussing here itself. Next question. This type of model also important. Which of the following is paramagnetic? Which of the following is paramagnetic? Very, very important model. So how to identify which is paramagnetic? If it has unpaired electrons, we can say it is paramagnetic. So option 1, that is first option, nickel carbonyl compound, that is tetracarbonyl. Option 2, it is iron tetracarbonyl. Option 3, it is vanadium hexacarbonyl compound. And option 4, it is chromium hexacarbonyl compound. So coordination number is 4, coordination number is 5, coordination number is 6, coordination number is 6. Now how to solve this type of questions? Let us see now the solution I will write here. Very, very important, this model. So question number 5, let us see now. First, identify the hybridations. So it has vanadium plus 3, so it is cobalt 6. So it is nothing but answer is this, because vanadium CO6, vanadium cobalt hexa is nothing, contains how many unpaired electrons? That is nothing but It is nothing but 23 plus 6 into 2, that is equal to 35 electrons. So this contains, because 2 and carbonyl compound, so 35 electrons. So it is nothing but what? It is paramagnetic. It is paramagnetic. So this is a question based on valence bond theory. Next question. Question number 6. One model. So different models we are going to get in the examination. So please see, all the important models are very, very important now. We are going to discuss. Next we have Fe F6 3 plus. Fe F6 3 plus has Fe F6 places 3 plus iron atom has dash hybridization C easily can tell it, hybridization comma with unpaired with dash, that is fill in the blank, unpaired electrons. How many unpaired electrons it contains? Unpaired electrons. So combination of two questions. So please see here. Option A, that is D2sp3, 4 unpaired electrons. Option B, it is D2sp3, 5 unpaired electrons. D2sp3 hybridization, 5 unpaired electrons. Option C, it is sp3d2, 5 unpaired electrons. And option D, it is sp3d2 and 3 unpaired electrons. Now, which is the right option? We have to check. Very, very important question, this model. So let us see now. Easily we can find out this answer. So solution, first we need to see whether it is D2sp3, because anyway it is coordination number is 6. Since coordination number is equal to 6, so it will have either D2sp3 or sp3d2. So since fluorine is weak field ligand, fluorine F minus is weak field ligand, so definitely it will undergo sp3d2 hybridization, outer orbital complex. So it is outer orbital complex and weak field ligand. So it is according to Hunt's rule. So according to Hunt's rule means sp3d2 hybridization. Very, very important. And now, what is the oxygen state of iron here? Iron plus this state. Plus this state means this d5 configuration. What configuration? D5. So it has how many unpaired electrons? D5 means 5 unpaired electrons. How many unpaired? 5 unpaired electrons. Since it contains 5 unpaired electrons, so option is C. So like this, you have to check the answers. Very, very important. So you should think all the 4 concepts important. Coordination number first. Second is whether it is strong field ligand or weak field. If it is weak field ligand, outer orbital complex. Outer orbital complex means according to Hunt's rule. So it is also according to Hunt's rule. So the pairing of electrons takes place according to Hunt's rule. So since the pairing of electrons takes place according to Hunt's rule, it will undergo sp3d2 hybridization, no overlapping. So, and next for finding number of unpaired electrons, see the configuration oxygen state of iron. Iron is in +3 state. Since iron is in +3 state, it has d5 configuration. It has what configuration? D5 configuration. As it has d5 configuration, it has how many unpaired electrons? 5 unpaired electrons. So you have to think of all these points in the examination. From all these points, any two or any one question they'll ask in the examination as options. So I hope it is clear. Very, very important, these type of questions. Please note down. Next question number 7. All the important models I'm trying to do. So same thing they can ask even questions like this. Very, very important questions. Next question. Which of the following complexes? Which of the following complexes, the following complexes will exhibit minimum paramagnetic behavior. Very, very important question. Minimum paramagnetic. In the orbital complex, they will have paramagnetism. So minimum paramagnetic behavior. So we need to check option A. It is FeH2O taken 6 times. Its coordinate number is 6. And outside it is +2. So ion is in +2 state. Next, option B. Manganese H2O taken 6. And it is +2 again. Next, we have option C. Chromium H2O taken 6 times and with +2 state. And next we have nickel H2O taken 6 times with +2 state. Now they are asking which of the following complexes will exhibit the minimum paramagnetic behavior. So minimum paramagnetic behavior means it should contain unpaired electrons more or less. It should contain less number of unpaired electrons. So out of which are the following? All the ligands are same. So we have to see the number of unpaired electrons. Whichever is having less number of unpaired electrons, that will exhibit least paramagnetic behavior. So the unpaired electrons of iron here, we can see iron +2 state. So N is equal to 4. So the first case, number of unpaired electrons is solution I'm writing here. So please note it down. So like this, since they are given same ligands, so solution you can see here easily, finding number of unpaired electrons, because paramagnetic behavior is related to unpaired electrons. So in the first case, that is option A. Now iron +2 state, so N is equal to how much? 4. Second case, option B, manganese +2 state, so N is equal to 5. N is equal to how much? It is 5. And third case, chromium +2 state, so N is equal to how much it could be, because +2 +2 +2, because this is water is weak field ligand, and moreover it is not contributing any electrons. So chromium +2 state, so N is equal to 4. And finally nickel is in +2 state, so nickel +2 state means what is the value of N, that is number of unpaired electrons, is equal to 2. So since nickel has 2 unpaired electrons, it is least paramagnetic. 2 unpaired electrons, it will exhibit minimum paramagnetism. So answer is fourth option straight away. So like this, you have to check. Maximum paramagnetic means manganese. Minimum paramagnetic means fourth option. Next, question number 8. Soon we are going to wind up this session. So please listen carefully, because these questions are very important for our understanding of the complex. So next question we have 2 more questions I'll do, then I'll wind up this session. The correct order of, it's very simple to answer this type of questions. the correct order of magnetic movements among is among the following is magnetic moment only spin. The following is spin only magnetic moment. Spin only. That is mu is equal to root of n into n. Option A, it is MnCl4 taken 2 minus greater than cobalt tetrachloride 2 minus greater than iron hexacyano, that is 4 minus. Next, option B, MnCl4 2 minus greater than FeCN taken 6 times 4 minus greater than CoCl4 taken 2 minus. Option C, FeCN taken 6 times 4 minus greater than MnCl4 2 minus greater than CoCl4 2 minus. And option D, final option, iron hexacyano, that is FeCN taken 6 times 4 minus greater than CoCl4 taken 2 minus greater than MnCl4 2 minus. So what is the basic concentration here? Correct order of magnetic moment. So magnetic moment is proportional to number of unpaired electrons. So that's why we should find number of unpaired electrons in first case, second case, and to find since magnetic moment is proportional to number of unpaired electrons, that is number of unpaired electrons, we can easily write number of unpaired electrons. So which is having maximum number of unpaired electrons will have magnetic moment. So greater magnetic moment. So straight away we can find the oxygen state of manganese here. So let us see the oxygen state of manganese in the case of manganese MnCl4 2 minus. What is the oxygen state of manganese here? Plus, if you know the oxygen state, easily you can find number of unpaired. So implies oxygen state is equal to x minus plus minus 1 into 4 is equal to minus 2. So x is equal to plus 2. So the oxygen state of manganese is plus 2 here. And cobalt is again x minus 4 is equal to minus 2. So cobalt is also plus 2. And x minus 6 is equal to minus 4. So implies x is equal to plus 2. So iron is also plus 2 state. So you know the states of manganese, iron, cobalt is plus 2, and plus 2. So now we can find out configuration. We can find out the configuration easily. Since manganese plus 2, we can write the configuration, whether it is D2, D3, D5. So write the electron configuration of manganese plus 2, cobalt plus 2, and iron plus 2. So easily you can find the answer itself. So option is first option. Why first option I got? Because manganese plus 2 means contains how many unpaired electrons? Manganese plus 2 contains how many unpaired electrons? Let us see now. So manganese plus 2 contains 5 unpaired electrons. So in this case, n is equal to 5. And cobalt plus 2 contains how many unpaired electrons? N is equal to cobalt plus 2 contains how many unpaired electrons? Let us see now. Cobalt plus 2 contains n is equal to 3 unpaired electrons. So you can see the configuration and you can write. And similarly, iron plus 2 contains how many unpaired electrons? It contains n is equal to, again it is iron plus 2, n is equal to 0, no unpaired electrons. So it has, now iron plus 2 contains how many? 0 unpaired electrons, because it is 3d5. So you can see, so as manganese plus 2 contains maximum number of electrons, so answer is first, second, and third. So first option. In this way you have to calculate the magnetic moment. Easily you can understand it. Next, question number 9. More one question we'll do, and then we'll wind up this class. So all the important models we have covered now. Next question, please note down. So previous JEE means question I'm writing here. The magnetic moment of the magnetic moment spin only of NiCl4 2 minus NiCl4 2 minus is option A, it is 1.8 Bohr magneton. Option B, it is 5.86 Bohr magneton. Option C, it is 2.82 Bohr magneton. And option D, it is 3.82 Bohr magneton. So it is simple. Straight away you can find how to find this magnetic moment. First, since m is equal to mu is equal to root of n into n plus 2, and where n is equal to number of unpaired electrons, since n is equal to number of unpaired electrons, so find number of unpaired electrons. To find number of unpaired electrons, we should know the oxygen state of nickel. So oxygen state of nickel is equal to oxidation state. Oxygen state of nickel is equal to x minus 4 is equal to minus 2, implies x is equal to plus 2. So plus 2 state, nickel is in plus 2 state. So you can write the configuration. So since nickel has plus 2 state, so it has how many unpaired electrons, implies n is equal to how much? N is equal to, since it has, you can see, so it has 2 unpaired electrons. How many unpaired electrons? 2 unpaired electrons. So magnetic moment is equal to mu is equal to root of 2 into 2 plus 2 is equal to 2 4s are 8. So root 8 is equal to approximately 2.82 Bohr magneton. So answer is third option. Simple. This is JEE Mains 2011 question. You can check, easily can understand, like these questions you are expected. Very, very important. Next question. So I hope it is clear. Last question of this session I'm doing now. Then we'll wind up this session. Then we'll start with new topic in the next session. So please listen carefully. So almost all the important models we have done. All the important models we have done. So please note down. Which of the following is true about the complex? Which of the following? This is statement based question. Which of the following is true about the complex? Is true about the complex? CrNH3 taken 6 times. Outside is Cl3. Option, first option. The complex involves D2sp3 conflict hybridization. Option 2, the complex is paramagnetic. Option 3, the complex is inner orbital complex. Inner orbital complex. Option 4, all the above. Option 4 is what? All the above. So you can easily guess this answer. This is also previous JE means questions. The complex involves D2sp3 hybridization since ammonia is strong field ligand. Ammonia is what? Strong field ligand. So it will undergo D2sp3 hybridization and inner orbital complex and paramagnetic. So all the four options are correct, all the three options are correct. So answer is all the above. Very, very important. So like these questions you will expect from valence bond theory. I hope you understood clearly. Very, very important all these questions. So with this, we are closing this session. I hope you understood. This lecture is very, very important. So you'll get questions like this only from valence bond theory. Please practice more number of questions from other materials. Thank you all.